Evening all. Greetings. I hope the transmission is okay. Give me a second. I'm sharing something in the chat. Hey Stan Smith, everybody else, Mark of Melbourne, everyone, greetings. I'm pasting something in the chat which I'm not going to play for fear of copyright, but which is worth watching to get a good gist of what passes as physics, science. You're seeing it right now. It's called Why Does the Universe Exist? Jim Holt. So watch that at your own in your own time. It's great. It's very interesting. It's also full of, well, it helps to see what silliness actually passes for science. When you hear it, well, see what you think. Now I'm going to read something. I hope the transmission's okay. I'm having it's looking a little bit jittery here. Okay. Now I'm going to read something. Patient devotes the intervals to some thoughtless pastime. He gradually loses the capacity for thinking, just as the man who always rides at last forgets how to walk. This is the case with many learned persons. They have read themselves stupid. That's from Schopenhauer. Now, let me screen share when the computer starts to cooperate. This is great. What I'm going to share now is very good. This fella. Let me just check that everything is okay in the chat, in the stream. Yeah, it looks like it is. I see lots of wrenches. I don't see anybody needing a wrench. So, good. Okay. For the rest of this, we're going to discuss how wrong the physicists have it, and science teachers, how wrong they have it. But before looking at examples of how they have it wrong, or even where they have it wrong, we're going to look at the fundamentals of why they have it wrong by listening to this fella. If you want to watch the video some other time, it's called Infinite Circle Equals Straight Line. That's right. So listen and enjoy.
Lies
Oh,
an error in the world of mathematics.
let me rewind because there was a little stutter. Okay, try again.
Infinity lies at the heart of a great deal of confusion and error in the world of mathematics, modern mathematics in particular. Mathematicians think that they can do things that they actually can't do. They think they can conceive of things that they actually can't conceive of. Let me give you an excellent example. Imagine a circle whose radius is infinite in length. Ooh, an infinite circle. Can you make sense of such a concept? Mathematicians might say, yes, of course, we can do all kinds of mathematics with this idea of a circle with the radius is infinite in length. Logicians and philosophers, and maybe some more careful thinkers, might say, actually, that doesn't make any sense. In fact, when you throw infinity into the mix, things start getting all wonky. One question illustrates the problem. Take any line segment on that infinite circle and answer this question. What is the curvature of that line segment? There are two possible answers. It is either the case that there is a curvature or there is no curvature. So if it's true that this line segment has a curvature, a non-zero curvature, whatever it is, then we are necessarily logically talking about a finite circle. You follow the curvature all the way around and you've constructed yourself a circle. It literally doesn't matter how big the circle is. It doesn't matter how small, just a tiny fraction of the curvature. If there is any curvature whatsoever, you are necessarily talking about a finite circle. But this presents us with a difficult problem. If there is no curvature, then that means we're literally talking about a straight line. Yes, so that means, in fact, a circle with a radius that is infinite in length is identical to a straight line. And in fact, as far out as you go along that straight line, there is never any curvature, because if there were any curvature, it would necessarily be a finite circle. Does that strike you as odd? A circle that has no curvature, logically, cannot have any curvature. I suggest if you're talking about a circle that has absolutely zero curvature, then you're talking about a line, and you're obviously not talking about a circle. Conceptually, this is, I would say, explicitly logically contradictory. There is no such thing as a line which is a circle. Now, I'm talking about Euclidean space here. I'll talk about non-Euclidean space in another video. But these concepts are logically mutually exclusive, and yet mathematicians don't treat them as such. This is just one counterintuitive example of the nature of infinity. Modern mathematics is shot throughout with counterintuitive conclusions like that, where we're talking about infinite sets. Say the concept of a set is necessarily a collection, a discrete collection of elements. They say, no, there are these things as infinite sets, that they're collections, but there is a never-ending amount of them. There isn't actually a finite amount, and yet we can collect all of them together into one discrete thing. If that strikes you as logically contradictory for the same reasons that there are no infinite circles, then good for you. You have a good head on your shoulders. However, infinite sets are stuck at the very root of modern mathematics. Set theory is considered one of the foundational areas of modern math, and it contains infinities, actualized infinities, shot throughout. Eventually I'm going to cover more of these logical paradoxes that are involved with infinity, but suffice to say, everywhere that infinity rears its head, when it's actualized, when it's completed, this idea of a completed infinity, causes logical errors.
Good man. Now, let's listen to this. And I am going to resolve some of the problems that I'm bringing up now, that the gentleman just discussed. Give me a second. Computer's not cooperating. Okay. Now, listen.
Now, I'll admit that the next question asked by the flat earthers threw me off guard a little bit. It's just not one I've seen asked in a flat earth debate before. Let's see what it was.
How do you explain light slowing down when hitting a denser medium and speeding up after leaving that medium for a less dense medium when the law of conservation of energy prohibits such observations?
Now, the only reason I could think of that they're even asking this question is that they're trying to debunk our understanding of refraction, because if they can debunk our understanding of refraction, it makes it difficult for us to use refraction as the reason we see photographs like this, which have...
Photographs like this. I will discuss this in 1 second. Let's just listen to Conspiracy Cat's quick little description.
This is the famous Chicago skyline photograph, which relied on atmospheric refraction for us to be able to see that over...
Which relied on atmospheric refraction to allow us to see that. Now this is the crux of this this hangout today. The globe believers think that a straight line is a section of any length, whatever length you say that straight line is, which is only it's a section of a circle, infinitely large, with a radius that's infinitely long. We'll come back to that in a second. The reason for this is so they can discuss things like things being on a flat, straight trajectory, but it really being a very bent trajectory. Here we have refraction. I'm going to hold this up, take a screen grab. Okay. And I'm going to describe. Here we have an object. This is the lighthouse on Rottnest Island in off the coast of Australia. Here's observer 1. He sees the light. The distance is supposed to be so great that he can't see the light. Refraction would cause either, if the denser atmosphere was below the eye of the observer, the light would bend down and the observer would not see the light. If instead the atmosphere was denser above the observer, which does happen sometimes, even though you think dense lower, no, sometimes not. There's evaporation, temperature, then there's a banding, and beyond that banding more humidity, and that causes more density. So in that case, when above the observer there is more density, the light bends into that density. That would be 2. In which case the light still does not reach the observer. Now a subjective experience of this would be, for one, this. This has a horizon. I've joined a dotted line between all 3 depictions. You have a horizon at some distance. That's yet to be determined. You have Rottnest Island, and you have, well, the lighthouse, and you can see the flashing light. For 2, where the light is bending up, you have the light bending up, which is raising the horizon. That's the water is being raised. The line is bending up. When you have 3, which is the line bending down, that's the light bending down, you have a lower horizon, you see. But what's really happening is the horizon is at the same point, but this would be what you might refer to as a superior mirage, which would be the water reflecting above the horizon line. And this would be an inferior mirage, which would be the sky reflecting on the water. So this is why you have the horizon lower down with a portion of sky, and sometimes you have, well, a ship above that sky. We've seen this, and sometimes you have a ship and just sky underneath. Other times you have a ship and a reflection of the ship. This is what's happening. Now what conspiracy cats would like to think happens is this. This version here, which is the distance is too great to see the object, therefore the line is bending around the curvature to the observer. 2 would be the line bending away from the surface, and 3 would be the line bending down. However, for number 2, if you look at the height here and the height here, you see that this is less height than this, which means the light has bent relative to the surface of the earth down towards the surface and then up away from the surface to miss the observer. And this would be, number 2 would be the straight line. Okay? That would be the straight line due to refraction of some mysterious type. Number 1, which would be seeing the object clearly and the conditions not being conducive to refraction, well, then the light is just generally bending around the surface of the earth to the observer. And number 3 is self-explanatory. That's conspiracy cats' excuse for seeing that image. Now let's go back.
Distance it was taken. But if you're still just a little bit confused about what the question actually was, let me use this picture to show you. What they're saying here is, as the light enters a glass block, it slows down, therefore it loses kinetic energy. And as it leaves, it speeds up again, gaining kinetic energy, thus breaking the law of conservation of energy. So let's see what the answer was.
There is a quantum mechanical explanation to this, but I don't think we have time to go into it. I don't have a whiteboard.
Well, I do.
Me too.
But let's let him finish answering his question first.
So the way that I picture it is that actually light travelling is essentially it hits an atom, that atom absorbs the photon, electrons within the atom are excited to a higher state, and then they drop back down and the photon is re-emitted.
So let's take a closer look here at what he was just saying. So the idea goes like this. The photon enters a glass and is absorbed by an electron, which is excited to the next energy level. When the electron drops down to its original energy level, it re-emits that energy as another photon. Now, the speed of the photons isn't actually changing here, but this constant process of being absorbed and then re-emitted makes it appear that the light is travelling slower through the glass. Now, that explanation would explain why the speed of light appears to slow down in the glass, even though the photons carry on travelling at the speed of light. However, there are some issues with it. And the biggest problem is this: when the electron falls back to its original energy level, the direction that photon gets emitted in is random. And so that will not allow us to have these consistent and predictable observations of refraction. Now, as the astrophysicist has already alluded to, there are quantum explanations for this problem. But in the description below, I've linked 2 interviews with 2 very, very high-level physics professors. If they go into this really, really deeply, I'd really urge that you go and check those interviews out. They're fascinating.
We'll look at one in particular. The second, the guy is his thinking is very fragmented. I'm sure he's counted a genius, but his thinking is fragmented.
What I'm going to do is give you the headlines and then hope you go and watch those. So at A level, we teach Feynman's sum of paths answer to this problem. We would say that a photon travelling from here to here actually gets from here to here by taking a whole infinite number of paths, and all those paths will travel at the speed of light. But as they intermingle with each other...
Remember, the man who was discussing the infinitely large circle was explaining the problem that the theoreticians, he said mathematicians, but in terms of theoretical physics, that's their function, to be mathematicians. The problems that they have when they discuss infinities. Now listen.
We would say that a photon travelling from here to here actually gets from here to here by taking a whole infinite number of paths, and all the...
An infinite number of paths. Oh, that's interesting. That's the kind of thing that gives you guys problems.
Paths will travel at the speed of light. But as they intermingle with each other, we'll get constructive and destructive interference. And what we'll find is that the constructive interference occurs along this line here.
The constructive interference happens, coincidentally, where the beam is. That's right. No rhyme or reason. None whatsoever. It just does. That's where it happens. It's not a filament that's been bent by the glass. Don't be silly. No, it's constructive interference that just coincidentally takes the path of the beam.
Just to see the light, and all those, the parts where all the other paths have interfered, we get destructive interference, and so we don't get to see the light. Now that might...
Now, he just said all of the other paths destructively interfered with by themselves, and we do not see the light. Now, for this I'm going to have to show a drawing, just bear with me, to show how wrong these physicists and people who discuss these physics have it. And it's kind of simple. Just bear with me. What I'm going to do is I'm going to draw a beam of light, not through a prism. Okay, don't worry about the prism, but it will show the problem with the prism too, or with the glass slowing down the refraction. There's a beam of light. It has a direction according to their theory. And when it goes through something that refracts it, well, it does a couple of magical things, like it starts being the same line, it staggers, and it takes a little bit of longer time than should. So this is a beam of light. The description is that inside, actually I draw another one, this time being refracted. The description says, well, this happens due to the refraction. Okay, don't worry too much about the angles. And the waves interfere and coincide, so constructively delineate the path of the beam and nowhere else. That's what he just said. The light does not go out anywhere. Okay, so remember the arrow, that's the beam of light. Now I've done an arrow, cast a shadow from it. It's the same line. I've cast a shadow, and I've cast an object. I've drawn an object to show one plane around that beam. Okay, that's this drawing. So this is just to show the angle at which this would be around. Okay, now here's the beam, there's its shadow. Here's a fan with all these 360, and you can subdivide as much as you like. And here's a shadow cast by this object. Now this object is a thought tool, that's all it is. It's saying, when you have a beam of light and you're looking at the beam of light, okay, and you're seeing the beam of light, and the mathematics is describing the beam of light with that direction and construction and destruction and what, but it's not discussing the beam of light that's falling to your eye from every single point of that beam and falling on the eye of anybody who's looking on that beam. And it can be looked at from all the various possible angles. This would be a set of, on one plane, angles of people that can look at the beam, but that's just one plane. We have another plane like this, so 360 like this, and we have another plane like so, 360 like so. All of this light is falling in these observers' eyes. How is it falling in these observers' eyes if it has not changed its trajectory and bounced back somehow? Because let's face it, here we have the beam, and now we have one observer who's looking at this region. He's looking at this region of the beam. He's focused on that part of the beam, the middle of the beam. So the light that's falling in his eye has gone this way and this way, whilst also continuing that way. Now obviously you can draw as many as you want. Their explanation is so infantile, it's absurd. But let's continue.
And a little bit fantastical. So a more classical explanation.
Now, I'm just going to rewind to listen to what he just said, which is this explanation might sound a bit fantastical, a bit made uppy, maybe, a bit ad hoc. Let's listen.
Have interfered, we get destructive interference, and so we don't get to see the light. Now that might sound a little bit fantastical, so a more classical explanation will be that the photon, which is really disturbance in the electric field, is going to have an effect on the charge.
Disturbance in the electric field. What's the field? Oh, I'm not quite sure, I'm sorry. Oh, do you mean the field is like the Force from Star Wars? Is that what the field is? We're not really sure what the field is. We just say that word to mean, well, something in which something occurs. It's like, oh, how precise.
Particles in the atom when it hits the glass, and those particles are going to give off their own electromagnetic waves, which are going to disturb the atoms next to those, which are then.
So there's the electromagnetic field, and then there are the electromagnetic waves which happen within that field. They can't really describe the field, and they certainly can't describe waves. Remember, they think light is a wave. Somehow they've forgotten to include the fact that light must be bouncing and doing a sharp angle at the speed of light without any loss to kinetic momentum or anything like that to come back to the observer, like somebody shooting an arrow and that arrow hitting them in the eye without slowing down at all, whilst also hitting the target.
They give off their own electromagnetic waves, which will disturb the atoms next to those, and so on and so on. So what we have through the glass is a huge number of different waves, all spreading out, and it doesn't look like that, right? Spreading out in all different directions, but again, interfering with each other, some
constructive, some destructive, and coincidentally, all of the constructive only in that beam, according to their theory.
Some destructively, and the path that we see here is where the constructive interference has taken place. Now,
that's interesting. Why has it taken place there? Is it because there's like a filament that directs where the light, well, should be?
Those waves that are being given off and propagating through the glass are travelling at the speed of light, but the apparent constructive interference, the apparent ray caused by constructive interference, does move apparently slower. It's very difficult. Links in the description. Anyway, let's have a look at the next one.
Very good. Links in the description. Now we're going to look at the links. I'm going to have to jump ahead a little bit. Oh, sorry. I'm going to have to jump a little bit because the first one, there's a little bit of preamble. Professor 1. Here we go. I'm just waiting for the computer to, yeah, there you are.
Okay, so here's the situation. 266.
Right. We don't need the preamble. We'll jump straight ahead. We're going to listen to the guy at the top.
I want to do a video about refractive index, N, because it actually has a symbol apart from anything else.
So, refractive index, N, part of the reason he wants to do this talk is because it has a symbol. It's like, oh, that's interesting. Was the symbol just completely arbitrarily chosen and given? Yes. Right, so it doesn't really have a symbol. It's not like something that's an inherent quality of it. Just something projected onto it so you can discuss it. That's right. Okay, then why did you say that it actually has a symbol? That's just silly. Let's go back.
Very shortly, you'll be able to watch the one from Professor Moriarty.
Whoa.
Whoa.
By the way, the other guy, the guy we're not going to listen to because he's a bit broken biscuits, is called Professor Moriarty. I'm pretty sure he's a Sherlock Holmes enemy. But might be wrong.
Video about refractive index, N, because it actually has a symbol apart from anything else, but also because it's something where we've done quite a lot of videos which mention refractive index, and we talk about the speed of light when it's going through a medium, through glass or something like that, and we talk about the speed of light slowing down, and invariably when we do that, there's this sort of firestorm in the comments to the video, all about people saying, but photons always travel at the speed of light, what's going on, why does the speed of light slow down, and so on. So I wanted to try and explain what's going on, and the fact that the speed of light really does slow down when you're going through.
Right. It's absolutely taken for granted that light is a photon. Could that be wrong? Yes. Oh, if it's wrong, then what? Then we have to start again. And that's right. They're going to have to start again. And I mean this seriously. They are going to have to start again. Some physicists have already started again.
In crude terms, if you measure the speed of light in a vacuum, you always end up with the same answer, 300,000 kilometers per second, or thereabouts, C. Okay? If you measure the speed of light in something else, air, glass, whatever it is, you get an answer. The refractive index is just defined as the ratio of those two numbers. So, for example, the refractive index of glass is typically around 1.4, which means that light travels about 40% slower in glass than it does in a vacuum.
That much?
Yeah.
I always imagined it was just like a minuscule change.
No, so in air, it's like it's a fraction of a percent. So air really is, the speed of light really is very close to the speed of light. But in a fairly dense material like glass, yes, it's about 40% slower in the glass than it would be in a vacuum. So I mean, it's responsible for all sorts of things. The reason why when you look through glass, when you look at a straw in a glass of water, you see that the straw appears to be bent and so on. So all these things to do with the paths of light being bent are all to do with what happens when light goes from one refractive medium with one refractive index to a medium with another refractive index. So, for example, from air to glass or air to water.
You wear glasses.
I do. So, and they wouldn't work if it weren't for refractive index, because that's what bends the light, right?
That's right. So he's seeing 40% slower than people who do not wear glasses. That's interesting.
Actually, yes, the lenses wouldn't work. So lots and lots of physics really depends on refractive indices. So this always comes up that people say, oh, well, so people are quite reasonably happy with the idea of waves and maybe the waves slow down. But then you start thinking about photons, particles of light. And there's this view that a photon always travels at the speed of light. And so when people start thinking about this and say, well, how can it be when you've got your photons going through, if you think of the photon picture, when you've got your photons going through glass, why is it that they take longer to come out the other side? So the picture a lot of people have, let me draw a picture for you. So the picture a lot of people have is I've got a material rather than a vacuum, so I've got lots of atoms in there. The atoms that make up, and maybe they'll be in a lattice if it's a solid, or they'll be randomly distributed if it's water, but there'll be just a bunch of atoms. So the picture a lot of people have is my particle of light comes in and kind of does a sort of pinball. That's the word I was looking for. So the picture a lot of people have is that the light comes in and does a sort of pinball thing of bouncing around, okay, and then coming out the other side. And that's
on a 2D plane. That's peculiarly interesting, but let's continue.
Makes sense, right? Because if this thing is still travelling at the speed of light, obviously now it's travelled a longer path to get out the other side, and therefore it should take longer to come out the other side. The problem with that is, if you think about it, take glass as an example, where you've got this refractive index of around 1.4. That means that the path the thing has to travel along has to be something like, instead of travelling straight through it, has to travel 40% further. That means it has to be sort of travelling on paths like this, right, in order to come out the other side 40% slower, because that's the angle that typically you have to be going for this path to be about 40% longer than the straight through path. Okay. The problem with that is that would mean that some of the light will do that, and some of the light will come in and bounce this way and this way and this way and this way, and then end up coming out that way. So what you'd expect for the light coming out the far side, in this case, is that the light should all be heading out in all sorts of different directions, just depending on...
Exactly. Heading out in all sorts of different directions. Now, just bear with me. I'm going to go back to Conspiracy Cats' video. We'll come back to this.
Next question.
Pause. Okay. We're going to go back and we're going to listen to one of the physics students.
Yeah, sorry.
Let me just get it to the correct point. One of the physics students explain what actually happens with light. Unfortunately for the physics student, he's explaining it as if what he was explaining was the direction of gravity. Okay, so just listen to the student, please. Now, we just heard the physicist explain how, well, if it was bouncing around like this in order to make a 40% longer journey, then, which would account for that 40% delay, then it would be coming out in all directions. Now listen to the student describe gravity.
Yes. So because of that, you can imagine if we're using arrows like in basic mechanics, you've got an arrow going down and then...
Now the arrow going down would be, in terms of light, the direction of the light, apparently.
Arrows in all other directions and an arrow going up. That's the...
Arrows in all other directions and arrows going up. Huh, that's interesting. So, the direction he's describing, which is gravity, causing further density lower down, that's the story, apart from when it isn't more dense lower down. You know, then they have a different story. These vectors, these directions that he's describing, in all directions, let me go back, listen.
Surrounding it. So because of that, you can imagine if we're using arrows like in basic mechanics.
Arrows like in basic mechanics, that's right.
You've got an arrow going down and then you've got arrows in all other directions and an arrow going up. That's the up arrow is the pressure, and
Okay, so the up arrow would be the source of the light. Okay, going in all directions. But he's describing gravity. He's not describing light. Now, the guy who's describing light, he could take the description for gravity and use it to describe light. Because if we've seen, any direction from which an observer is looking at the beam of light is receiving a beam of light, beams of light at their ocular processors, their eyes, no matter what directions or all possible directions. But the story of light doesn't include that. The story of light just discusses, well, this single trajectory, it doesn't discuss all of the other possible directions. And what I'm saying is, if they wanted to, they could take this explanation for gravity and replace the word gravity for light. They could. Oh, sorry. Now let's go back to the professor.
Okay, so here's the situation.
What's the situation? Let's go.
Instead of pinball.
It's very interesting how much touching of the nose they do. This and the other professor do a lot of touching of their noses whilst describing things. So let's go back to here.
For the light coming out the far side, in this case, is that the light should all be heading out in all sorts of different directions. Just depending.
You hear? All sorts of different directions, exactly. And it does. Except it has a lot more coherency in that one beam. But that one beam is energizing all of the other filaments we have in the real world, which transmit information, including to observers. Oh, good Lord, it's explained in the Book of the Sun.
What it happened to bounce off last. And of course, that's not what happens. If you shine a laser into a piece of glass, then the laser beam comes in one side and it comes out the other side. And
it's visible from any point of view, which means it's also reaching out to that point of view. No matter what direction that point of view might take to the location of the laser.
Laser beam still all pointed in the same direction. So this picture really doesn't work of thinking about this game of pinball going on, because if you start doing that, that should mean that the light really should be spreading out in all directions.
And light does spread out in all directions. So he has just given an explanation and said, but this explanation isn't actually quite right, because if it was, then light would be going out in all directions. Excuse me, Professor, light does go out in all directions. It just has more coherency in the beam, in the filament, in the ray.
I think of it more as, instead of pinball, wading through treacle or honey, and I'm just walking more slowly because it's harder for my legs to move through this viscous material.
But then you have to get, okay, so that's fine, but then you have to get, okay, so that's sort of a macroscopic view. Now let's go down to the microscopic view. What's happening?
Right, so he's just been describing a process that he's either now labelled as macroscopic, the guy walking through treacle as if he was a photon of light, okay, or he's referring to this pinball system as a macro system. Say, oh, that's very flexible use of the word macro, so that you can then say, now let's look at the subatomic, at the micro. Like, wait, that pinball thing was micro.
Light doing when it interacts with the atoms. And there is another possibility, right? The other possibility that could be going on is, again, here's a bunch of atoms, and it could be that the light...
Now, notice the reference, or yeah, the reference. It could be this, what could be going on. That's why I've called this fake it till you make it. They don't know. All they know is that mass, things that have mass, in fact the entirety of the world, has this thing called electromagnetism. It has this. And things interact with this electromagnetism. Atoms must have electromagnetism. when we experiment, it appears like they do. Except the theory of the atom is a theory. The observation of the electromagnetism is true. The observation is true. It's just not true that it's an atom that's causing it or that has it.
Coming in, it's getting absorbed by one of these atoms. It then sticks around for a little while until the atom chooses to re-emit the light again and send it on its way. And that's sort of, at the microscopic level, that's this sort of what's going on in a twinkling picture, that things are just being delayed as they're going through. Again, there's a couple of problems with that. I mean, we know that atoms do absorb, atoms on their own absorb light, so this picture sort of works, that atoms do absorb.
No. That electromagnetic vortices do absorb light. We do know that. That's true. They do. It is true. But they say, oh no, it's the atom. No. It's the electromagnetic array. That thing you can't describe, which is described in the Book of the Sun as an array. It's a system that has structure, like an array of antennas.
Right? And then they'll re-emit it sometime later. There's two problems with that. Firstly, atoms tend to absorb light at very specific frequencies. And so you would then expect your refractive index to affect those particular frequencies a lot because the atoms are absorbing light at those particular frequencies, and other frequencies not very much at all. So that means that the refractive index should vary dramatically depending on exactly what wavelength of light you're looking at. It doesn't happen that way. Refractive index does depend on the wavelength of light, but generally rather smoothly rather than this very kind of discrete way. The second problem with that is that is, again, fundamentally a kind of a stochastic process, a random process. How many atoms did you happen to bump into in your way through? How long did each atom happen to delay the light for? Because how long an atom takes to, when it absorbs a photon of light, how long it takes to re-emit it again is just a random process. That means that how long it takes a photon to get through should just depend on, in a fairly sort of random way. Sometimes they'll get through very quickly, sometimes they'll have more of a problem. Again, that's not what you find. When you measure that how, you first turn on a light through a block of glass and measure when the first light comes out the other side, it's always the same amount of time. So again, you can't have any kind of stochastic process like that going on.
All right then, you've convinced me that they're wrong. Tell me what's right.
All right, this is where life starts getting very complicated.
So, all of the explanations and descriptions he has given up to now are all of them not what it is. That's right. But it's all priming. It's all saying, remember when you learned about this, and remember when you learned about that, and remember when you learned about this. So guiding your thinking. Like I said in my previous hangout, don't let people guide your thinking. He's guiding the thinking. Remember these things, now continue. Look down this avenue. The things he's pointed out had nothing to do with it. He said, no, those things are not it. Now I'm going to tell you what we think is it. Listen. And now it's when it gets complicated. I wonder if math will come in now.
Yeah, I said that wasn't complicated enough. This is where things do start becoming a little more complicated, because now we have to start thinking always with these microscopic systems. You can think about them classically, or you can think about them in terms of quantum mechanics. And at some level, they're sort of both getting part of the picture. It's just like, you can treat light sometimes like a wave, sometimes like a particle. So we need to think about both possibilities. So let's start with the classical end of things, the wave end of things. What you've actually got in your solid is a whole bunch of atoms arranged in a lattice.
What you've actually got, this is theory. It's not true. But it's now describing the truth of things. So he's saying what you've actually got is this. Before he was saying, so imagine if you had, now it could be that. Now he's saying what you've actually got. It's like, interesting.
So light comes in as an electromagnetic wave. Okay, it's basically a varying electric field. That's going to jiggle all the atoms in this thing because they've got charges and so on. So
that's going to interfere with all the charges that coexist, that are sharing existence as a piece of glass.
Electrons are going to get pulled around by that electric field as it goes past. And that's going to, when you then start moving these electric charges around, that means that each atom is going to respond by producing electromagnetic waves of its own. Okay, so the waves come in, they start jiggling the atoms around, which means that each of the waves will then start kind of oscillating in sympathy with the wave that's causing it. And it's the superposition of the wave coming through, the undisturbed wave, and all these sort of waves that are being created by the atoms that make up the material. When you add all those waves together, you end up with the wave that's actually propagating through the glass, and that wave is the one that's then travelling at less than the speed of light. Okay, so even if each individual wave that you're producing could be travelling at the speed of light, the kind of the superposition of them then creates something that's actually sort of is retarded. It hasn't travelled quite as far as you expected it to. So the net effect of adding the light that comes in with all the light that you end up generating through jiggling all the individual atoms produces this picture of the overall wave that you end up with by adding all that lot together is travelling slower. And the problem is, if you actually want to do what, rather than just sitting here waving your hands about, if I actually wanted to show you that actually the speed that of the net result of adding all these waves together is to produce a wave which is travelling at less than the speed of light, that's a lot of maths. And so you can do it.
So, if you wanted to really see whether or not what he's saying is right, you could do the math. That's right, following the rules of behaviour for the various different factors in the equations, you'd arrive at the conclusion that he's told you is correct. Oh, good Lord! Would this be the mathematics that has a straight line as a segment of a circle?
Solving the equations of what happens if I add all these different waves together, each with different phase shifts and so on. But it's just a mathematical mess to get to that point.
So when Barry, the beam of light, entered a piece of glass and started making all the bits of glass start jiggling, how did that then affect Barry, the beam of light?
It didn't, except, well, some of Barry's energy was lost because actually it was being used to jiggle all these other things around, so some of that light would have been lost for that reason. But it was then all these friends that Barry had created in the process, and the sum of all those different waves then created the net effect, the net wave that was travelling through the thing, which was then a wave which was travelling at less than the speed of light.
So Barry, the beam of light, jumped off the stage, and all the friends, they all let him do some crowd surfing. That's what happened. You can see that, you can picture that, because he just actually used the word picture. I'm going to go back to the point where he says the word picture.
Wave is the one that's then travelling at less than the speed of light. Okay, so even if each individual wave that you're producing could be travelling at the speed of light, the kind of the superposition of them then creates something that's actually sort of is retarded. It hasn't travelled quite as far as you expected it to. So the net effect of adding the light that comes in with all the light that you end up generating through jiggling all the individual atoms produces this picture of
produces this picture. Your brain goes, what's a picture? Oh, it's a thing that you see. Oh yes, I see. So all the mathematical equations you can translate, whatever they are, however long they are, however many days and days it might take to do all of the mathematics. I can picture the beam, and the maths would say the beam. That's okay. You see, this is how teaching is done.
Overall wave that you end up with by adding all that lot together is travelling slower. And the problem is, if you actually want to do what, rather than just sitting here waving your hands about, if I actually wanted to show you that actually the speed that of the net result.
So if I actually wanted to show you the net result of the various different speeds involved, I could, with math.
Adding all these waves together is to produce a wave which is travelling at less than the speed of light. That's a lot of maths. And so you can do it by solving the equations of what happens if I add all these different waves together, each with different phase shifts and so on. But it's just a mathematical mess to get to that point.
So when Barry, the beam of light, entered a piece of glass and started making all the bits of glass start jiggling, how did that then affect Barry, the beam of light?
It didn't, except, well, some of Barry's...
It didn't, except it did.
It was lost because actually it was being used to jiggle all these other things around, so some of that light would have been lost for that reason. But it was then all these friends that Barry had created in the process, and the sum of all those different waves then created the net effect, the net wave that was travelling through the thing, which was then a wave which was travelling at less than the speed of light.
What is it about all those friends, all that extra waveness that was summed onto Barry, that retarded him rather than enhancing him and making him faster?
In fact, you can, in very peculiar circumstances, create things where you end up with a wave which is travelling faster than the speed of light in vacuum. Physicists tend to try and keep quiet about this because it makes life complicated. And it turns out, actually, you don't end up, everyone gets worried because at that point you end up saying, am I breaking laws of physics? Am I breaking relativity and so on? Actually, you don't, because then you start saying, okay, so can I actually transfer any information through this medium? Can I use this to actually get information to travel faster than the speed of light? And the answer is you can't. Because there's two types of speed for a wave. There's a thing called its phase speed, which is what actually I've been talking up till now about. There's also a thing called its group speed. And the group speed is if, for example, you wanted to produce a little pulse of light, how fast would that pulse propagate through? And the group speed, and that's what you'd need if you actually wanted to send information, because if I wanted to do Morse code or whatever, I've got to send little pulses of light through that. The group speed always ends up less than the speed of light. The phase speed, under peculiar circumstances, can end up faster than the speed of light rather than slower than the speed of light. So that's the classical explanation. Okay, the simplest version of the quantum picture is to say actually it's kind of the same thing, because the weird thing, so photons have really weird properties, right? For example, if you do this experiment of having two slits and you shine light through it.
I know something else that has very weird properties. Like being able to be more than one location at any one time, physically. That's Father Christmas, Santa Claus, that's right. Yeah, so let's go back and listen to these weird properties.
To say actually it's kind of the same thing, because the weird thing, so photons have really weird properties, right? For example, if you do this experiment of having two slits and you shine light through it, you end up creating an interference pattern, just because the light that went through one slit interferes with the light that went through another slit. So it's kind of the same, actually, story we were talking about before, that you actually end up with light travelling through different paths, interfering and producing a new phenomenon. But actually, if you think about things in terms of photons, even if you have a light source which is so weak that only one photon is going through at a time, you still create an interference pattern. And the only way we can understand that is if the photon actually went through both slits. So one particle manages to go through both slits at once. And that.
Or one burst of energy, which they class as a release of one particle. That burst of energy happened to hit two filaments. Oh, good Lord. You mean you strummed two strings at the same time? You mean you hit a splayed rope? You sent the energy here, you plucked here, punk, but that was divided and it hit two sides of the slit? Good Lord. There's no way of explaining it, is there? Other than what the guy just said.
This is getting us into this weird quantum mechanical world. Okay, we can do the same thing with our solid of saying, okay, so if I think of my light as a bunch of photons, I can actually think of a photon following every possible path through this thing. And as it goes through, it interacts with each of the individual atoms, gets re-radiated, and what I see as the kind of the final light that this is producing is the superposition of all those things. The superposition of the light, the photon that came in undisturbed, but also all these other paths that it followed interacting with all the atoms on the way through.
And all of them went straight back into the path that the Barry the Beam surfed on the crowd. All of them interfere back to coalesce at that point through the glass, where you can see beam outside of the glass, beam inside the glass. Huh, it's interesting.
It's basically the same as the classical picture, where each atom is sort of producing its own version of the light. Here it's just thinking about the photon following every possible path, and then those photons, that photon by following every possible path, ends up interfering with itself and creating a net effect of light that's travelling slower than the speed of light.
Where do you draw the line, though? If our photon is going through every possible way, and we add up the superposition, every possible way seems like an infinite thing. It could have...
That is, yes.
Remember the chap at the beginning with infinities and mathematics? But that seems like an infinite. It is. Oh, in that case you're lost, aren't you? You're describing something you can't describe.
It's clever how a photon manages to follow every possible path to get to where it's going. Nonetheless, that seems to be, when you do the maths of say, what would I expect to see if that's the way...
When you do the math to say, what do I expect to see? Well, it depends on what parameters you've set out in your equations.
Photons were behaving, and then look at the real universe, you find actually that's the way the real universe works.
I understand.
That's the way the real universe works. Wait a second. You forgot about all of the other beams that the photons must be taken from, well, the beam to the eye of the observer. See light going that way? Beam, eye of the observer. Ooh, beam, eye of the observer. Here, beam. Oh, eye of the observer. Here, bunk, eye of the observer. You're forgetting about all those beams.
You gave two scenarios there. This classical one,
Yep.
You know, the jiggling and the adding of the waves and this quantum one, which is a bit more mind-bending, but nevertheless the maths works.
It's a bit more mind-bending, but nevertheless the maths works. Like, wow, you know, and I'm not joking, folks. If you wanted to, you could work out the math on how, in fact, it was done, how long Santa has to develop gifts at every Christian home in the world. You can do the math to see what period of time he has in each home. Obviously, he must dilate time, so he's got long enough to do it, otherwise he'd be setting fires in all of these homes, that much friction, like, come on. So, you can work out the maths. And the guy just said, well, yeah, very complicated, but no, never mind, the math works out, so must be real. That's what you're supposed to infer. Like, oh, wait, you can do the math for Santa Claus on how long he has in each home. You follow the same logic, which says, if the math is coherent and arrives at a pretty good conclusion, then it must be true. It must be describing something true. Some of you joined late, didn't hear me reading the quote from Schopenhauer at the start. Please, at the end of this, go and watch it. Go and listen.
Works for both of them.
Yes.
I accept that. Which one is actually happening?
So that's the problem with physics, right? Is that physics, what we're doing is we're modeling reality.
Here we have some truth. Listen carefully. We are modeling reality.
There's one reality, and you can have multiple models.
There's one reality, you can have multiple models, including contradicting models. That's right. It used to be thought that light was a crepuscule, a short little dash. And then it was thought, no, it's not a dash, it's a particle. And then it was thought, no, it's not really a particle, it doesn't seem to behave like a little bullet would. So it's a double thing, a particle that has the ability to behave like a wave. It's a particle, but if you say a wave is something that behaves like a wave, then it's also a wave. The particle behaves like a wave, so the particle is a wave.
And sometimes the models are exactly, or as far as we can tell, there's no, the models are entirely right. In other cases, each model kind of captures some aspect of reality. In this case, you can sort of explain the whole thing in terms of the quantum model. There are things you can't explain in the classical model.
Now, the quantum model is the one that needs the most amount of belief.
In that sense, the quantum model is more right. But actually, the classical model is very helpful because it's much easier to picture, and actually you don't end up...
See? Although the classical model is also wrong, as I've illustrated with the number of beams that must exist between the beam, the ray of light, and all of the observers. Okay, all those beams. They're not waves. Okay, we would only see a white fog if light was a wave. That's all we would see. Never mind out of phase, not actually cancelling and all silliness. Okay? We know. if you think about it, you realize, like, hey, I'm looking at this laser, and that guy's looking at this laser, so there must be light going from the laser to that guy's eye, just like it is to mine. Huh. But the descriptions describe only the direction of the laser. What about the direction of the photons that are going from the laser to my eye, or the wave that's going from the photon from the laser to my eye and everywhere? No, the quantum explanation is the best, but the classical is the easier to get a picture of.
Mind-bending things of one photon following an infinite number of possible paths and those kinds of things.
So you see, the one, I'm going to go back. Listen.
All right. But actually, the classical model is very helpful because it's much easier to picture.
You see, it's very helpful because it's much easier to picture. Okay, but
actually, you don't end up with these mind-bending things of one photon following an infinite number of possible paths and those kinds.
The true one is the one that's literally impossible. The other one, which we know is wrong, is just a good way of imagining it. But what you're imagining are fundamentally and profoundly wrong ideas about light and waves.
So actually, a lot of the time it makes sense to think about things in terms of classical physics, just because it's soluble, we can understand what's going on, we have a physical intuition for what's going on. But once in a while, you have to delve into the quantum mechanical explanation of things. Just to mess things up still further, there's another quantum way of looking at this, which is there's and again, it's this question of coming up with ways of modelling things. So I've just talked about two ways of modelling things. There's another way of modelling things that says actually a system that's a kind of a lattice or whatever that's in your material, and the light travelling through it is completely different from just light in a vacuum. And so actually we shouldn't just think of, light in a vacuum we can explain as a photon. This combination of light plus the lattice and all the way that the lattice can be made to jiggle is a completely different system. And when we come to solve that completely different system, maybe we'll come up with a completely different particle rather than a photon.
Gibberish. Let's listen again how he explains that. Well, in a vacuum, light is a photon. You mean if you did the Young experiment, the double slit experiment in a vacuum, it wouldn't split into the various different filaments or wave?
It's another way of modelling things that says actually a system that's a kind of a lattice or whatever that's in your material, and the light travelling through it is completely different from just light in a vacuum. And so actually we shouldn't just think of, light in a vacuum we can explain as a photon. This combination of light plus the lattice and all the way that the lattice can be made to jiggle is a completely different system. And when we come to solve that completely different system, maybe we'll come up with a completely different particle rather than a photon as the particle that's associated with light.
Or an entirely different mechanics, as described in the Book of the Sun, and as further described in my next book.
Physicists who study these systems have actually come up with a different way of mathematically formulating these things, where there is a different kind of particle, a thing called a polariton. And a polariton is this complex combination of the oscillations of the electromagnetic waves of the light and the oscillations of all the stuff in the material it's passing through, combined together produce this kind of particle. This kind of particle, the polariton, has mass, and because it has mass, that means it travels at less than the speed of light. So if you want a different way of thinking these things, but also a quantum mechanical one, is that your photon comes along, when it enters this medium, the maths that you're solving changes, and so actually the particle changes, and instead of being a photon, it becomes one of these things, a polariton. The polariton bimbles along at a bit less than the speed of light, and of course when it comes out the other side, then once again you're solving the regular equations of light in a vacuum, or light in air, and then...
Wait, when it comes to the other side, that's when it violates the laws. When it goes in, it's okay, it just loses momentum, kinetic flow. It loses, it's like running into the ocean, you slow down. It's only when it comes out that it then violates the laws of thermodynamics. It's only then, but it just glosses over that. Listen.
These things, a polariton. The polariton bimbles along at a bit less than the speed of light, and of course when it comes out the other side, then once again you're solving the regular equations of light in a vacuum.
You see, when it comes to the other side, it forgets about its mass and becomes super photon. Just a boom, takes off its tie at the door. But it's easy to visualize, see? It's easy to get a picture of.
Light in air, and that means that you can then treat it as a photon again, and it scoots off at the speed of light again.
How do you expect me to edit this?
That's it, that's the end. Now they joke about who's going to edit the video. Right. The reason I'm showing all of this is so that people can start to understand, and you guys watching, you can pass this on. The things that people have taught have molded their brain into processing the world in a certain way. When they see something that goes against what the brain has been processed, to recognize, to absorb and accept, when they see something that jars with that, they don't absorb it. That's what I'm going to show next. It is literally cognitive dissonance. And I'm referring to this. This is a part 2 from Peter and Pete. Come on, computer. Okay. I'm going to play it without the audio. And there are people, despite seeing this, having seen the first one, they just cannot accept what they're seeing because their brain has been molded in such a way as to not be able to take it on board. Even though they're seeing it, it's not CGI, it's just... Anyway, here we go. And it's real time. A small piece of dyed black softwood veneer. It's solid, but it's very light. Put that there. It's non-sticky. Okay, so it doesn't stick to the plastic. No, that's right. And the magnet holds it in place with, well, the steel nut, of course. And when the magnet stops having contact on the steel nut, then it stops having contact on the wood because it doesn't have any pull on the wood. It's wood. Wood's not magnetic. And before this, they showed it with copper, which is also not magnetic. Now, people might say, maybe the dye has some element of magnetic compounds. Like, no, whatever, don't be stupid. You can't use that excuse with the copper. So, we improved our earlier design and removed the inner lining of the compression fitting and the rubber seals installed inside the cap and used PTFE tape. PTFE tape is plumbing tape. Plumbing tape is used, well, so that there won't be any leaks, including in gas pipes. So really no leaks. That's better. We want to ensure we have a good seal and no leaks. Because obviously people couldn't accept it when it was, even though the excuse is ridiculous, with the copper, oh no, your seal, it mustn't have really been a vacuum. Regardless of what your compressor told you, your vacuum pump, regardless of that, it mustn't have been a vacuum. Oh well, did it like this now, are you still going to say it's not a vacuum? And the thing, like with the guy who was talking to the physicist, he could have questioned him and said, how do you know whether any of what you're saying is true? And the guy would have had to admit, well, I don't know that any of what I'm saying is true. So the people who are critiquing this, they could replicate it. They could just, repeat it themselves. So he puts the camera on the tripod, and then there'll be no more motion sickness. So now it's showing the setup. There you go, there's the pump. It's dropping. Vacuum pump was left on for well over 5 minutes. Okay. And dropping. Yeah. Okay. Wonderful. I'm not going to play the audio, but there's no leaks. And now, of course, he drops it, and lo and behold, the metal falls faster than the piece of wood. Now, these are the things that physicists should be doing. They should be doing this in physics lessons at high school, instead of avoiding doing this and explaining something that's patently false, like demonstrably false. Let's get the footage, original landscape orientation. There you go. Let's watch that one more time, but slowed down. There goes. Oh, look. Oh, look. Huh. Hot diggity damn. Could have guessed it. It's very clear the heavy object fell at a faster rate than the lighter object. Here's a comparison of the rate of fall for both objects. Huh. It's interesting. As both objects fell, the gap between them increases. Or increased. This means objects do not fall at the same rate in a vacuum. That's right. So our view, heavy objects will always impact the ground first. Now, here's where I, being me, I'm going to, I'm going to go back. And I'm going to say, only in broad terms, if we look at the experiment done by Dr. Zaz at the Bremen Institute, the lead fell slower than the aluminium and the carbon and the beryllium. So Xavier, heavy objects will always impact the ground first. No, the lead didn't. The lithium, which was the lightest of all, fell slower than the lead at first, and then the lead started to fall slightly slower than, both of them fell at almost the same rate as each other, whilst the other objects fell faster. We can't say how much faster because there's a bottom of the capsule. So, in his further investigation, and lo and behold, the Bremen Institute will not allow people to repeat the test and do further study. Doesn't matter. The House of Cards is coming down because people can repeat these experiments themselves. They can do this at fairs. They can take these out to street activism sessions. So, good job. And with that, I'm going to look in the chat, make sure everything's okay. I'm going to quickly scan to see if anybody doesn't have a wrench and give them a wrench so that they can comment freely. Oh, I see somebody without a wrench. GPS. Right, Antonio, thank you for the offending slide the other day. I have family things to do. We'll watch this tomorrow. Okay. Okay, well, you can have a wrench. Add moderator. Sensible, very good points throughout your hangouts. I tell you what, I'm not going to read all the comments, especially the ones that are heaping praise. But thank you, I appreciate that. Resemblance of truth. Okay, thank you. Hangout fine, very inside. Okay. I said I wasn't going to read, but there's lots of comments calling me all kinds of horrible names. Not really, but I mean, there might be, I don't know. Zenboy 2000 Rise hand. Don, you're watching Ken Wheeler's latest, that's Theory Apophasis. It struck me, although I haven't heard him literally say it, he's describing magnets as a lens for ether. Sooner or later he started describing them as filaments. You know, I told him to read my book, but, you know, I don't know. Right, give me a second. What I'm going to do, one last time before I go, is I'm going to reread no, I tell you what I will do. Or will I? Yeah, no. I will reread the Schopenhauer. Just give me a second. And then it's bedtime for me. Well, then, those of you who do Hangouts will know, then it's wind down and find something relaxing to either think about or consider, contemplate. 1 second. Okay, here we are. Schopenhauer, some of his writings a tad dark. Well, not really dark. Very profoundly pragmatic. But the one I'm going to read, and some of them highly humorous too. So I'm just waiting for the page to load. And I'm going to reread. In fact, what I'll do is I'll paste the link in the chat, and then people can read some of his quotes. I'm not going to read all of them. Just going to read the pertinent one. In fact, I'm going to read two. I jotted one down so I wouldn't have to scroll around too much. Okay. Type X and the name of someone to whom you think this might apply. The person who writes for fools is always sure of a large audience. That's just... The person who writes for fools is always sure of a large audience. Right. Okay, here I have it. Copy. Now go into the chat. Second. Here you have in the chat. Paste. Just a link to some Schopenhauer quotes. And now, let me go back to this. And I'm just going to read it again when my computer starts to cooperate. Okay. Just bear with me while I find it. It won't take me long. Okay, here we are. We looked at conspiracy cats. We looked at physics professors. We looked at a description of mathematics and how wrong it is. And then I will, after this, I will point something out that's just so clear that the people haven't pointed this out before. It's just astounding to me. But first I'll read this. When we read, another person thinks for us. We merely repeat his mental process. In learning to write, a pupil goes over with his pen what the teacher has outlined in pencil. So in reading, the greater part of the work of thought is already done for us. This is why it relieves us to take up a book after being occupied with our own thoughts. And in reading, the mind is, in fact, only the playground for another's thoughts. So it comes about that if anyone spends almost a whole day in reading, and by way of relaxation devotes his intervals to some thoughtless pastime, he gradually loses the capacity for thinking, just as the man who always rides at last forgets how to walk. This is the case with many learned persons. They have read themselves stupid. Now, when you do a degree, you're reading for, so I did a degree in philosophy. I read for a degree in philosophy, or I read philosophy. Whatever it is that you're doing, even if you're doing very practical things, so if you're doing a degree, you're reading. That's what it's called. That's an aphorism. Anyway, the people who get firsts at university are the people who have been doing exactly what Schopenhauer says makes people stupid, reading all day, and then at the end of it going, whew, I'm glad that's over. All that they've done is been a playground for the thoughts of other people, but they think that now they're intelligent. So instead of sitting and going, whew, that was heavy, I'll have a small break and then I'll really sit and ponder what I've read, because now they're mentally fatigued, they go, oh, I just want to watch Jackass or, I don't know, Real Housewives or something just vapid. And they become stupid. And you'll find that so many of the world's highest level thinkers, like clear thinkers, people who can see things other people can't see, they either didn't get a degree or didn't do all of the reading that was instructed for their degrees. So now I will point out something that's very simple regarding the circle, the infinitely large circle with the infinite radius. You see, the explanation for a straight line, according to mathematicians, and that's the area, the form of mathematics that's used by theoretical physicists. Okay? It's not arithmetic, obviously. It's more like algebra. Well, it is. It's an extended form of algebra. But anyway, their description of a straight line is not, well, a straight line. Something that would be straight if you had two of them buttered up and you, well, turned them 45 degrees or 90 degrees each. If they were buttered up continually, then those would be straight lines. If one was bent or if both were bent, well, there would be a point where they would not be, well, buttered up. Instead of having that as an explanation, the explanation is a straight line is in actuality, even though what they're now going to describe, or I'm now going to describe mocking them, but not really mocking them, actually saying what they say, is in actuality a section of an infinitely large circle. What do you mean infinitely large circle? Well, a circle whose radius is infinitely long. Here's the question that every single mathematics student and every single physics student should say immediately. Now, some of you will remember, I'm going to come back to that question, some of you will remember being at school and either being kicked out for asking questions or somebody in your class being kicked out for asking questions. So being asked to leave the class for asking questions. You see, when you ask a question, you can point to a falsehood. For instance, what I'm going to ask now. This infinitely long radius, is it straight? If it's not straight, it's not a radius. The radius can't be a segment of another circle that's infinitely long to serve as a radius, because, well, then it's not a radius. See, that simple question. So if you've studied mathematics and you haven't said, there's this silliness about an infinitely large circle with an infinitely long radius, and the straight line being a section of that circle, which would have necessarily an element of curvature, which, by the way, you could work out to be exactly the same as any other circle, including the most minuscule circle, because all of them have 360 degrees. So you could, divide it into seconds, arc seconds, blah, blah, blah. This radius, it must be straight. Therefore proving that the idea of the straight line being a section of a circle is false. Thank you very much for your time, folks.